Okay, it's my great pleasure to introduce Gabriel-Dominique Marleau. So the French name is difficult to pronounce the French name, so maybe we can just call him Gabriel. And actually he got his PhD in 2016 at the METIS. And he did his postdoc in Germany and Switzerland at a few places. And actually, so he stayed with Shani for 2 years in Berlin. Okay, then anyways, now he's in Duisburg. Okay, and his expertise is maybe radiation hydrodynamics, formation of the planets. I mean, I talked to him. Okay, so how can I tell them to tell you about his expertise? Anyway, okay. should I tell the idea to you or not?
As you wish.
Anyway, okay, so let's go ahead and talk. So please welcome the speaker.
Thank you very much, Hiro, for this very kind and funny introduction. So for your very kind invitation to come and visit here. It's a pleasure. Thank you to you all for coming. And I've heard there's a range of backgrounds in this room, so maybe cosmology and galaxies and high, low energy, whatever. So not just planets. So I'll try to start a bit more generally at first. But so, as Bern is where I had the pleasure of meeting Tami, and I'm at Duisburg, is the institute basically in the middle. And we're going to be looking at accretion-tracing line emission from gas giant planets from the observational side, but also from the theory. So I'll try to give sort of an overview and some specific results. So watch out, it will be at widescreen. Okay, high contrast. Let's start with some statistics. 200 billion. What is this number? Somebody have an idea? Somebody want to spontaneously say something? Yes, somebody's smiling? No, okay. Yes, that's right. So, or even 10 times more. I don't know. You're the expert, probably, not me, certainly. So it's the number of galaxies in the observable universe. Very good. That's an easy one. Let's keep going. This is going well. Next number, 1.4 billion. This could be many different things. Number of stars studied in detail by the Gaia satellite. So it's the billion-star observing telescope. It turns out about 1.4 billion stars in our galaxy, basically. Yes. 6,400 going down in orders of magnitude, as you can see. What is this? Yes, that's right. Very good. The number of confirmed exoplanets, so extrasolar planets, planets around other stars other than the sun. And this number is growing, but it's a slight range of orders of magnitude between these big numbers and these smaller numbers. Now let's keep going. 4. Well, okay, north, south, east, west, 4/4 of an hour per hour, right? It could be anything. But it's the number of known accreting gas giants in a disk around their host star. So this is a very small number compared to these other numbers, which is a reflection of the fact that it's still a very young field studying forming planets, so planets as they're growing in mass, compared to the number of known planets, the number of course, older stars and numbers of galaxies. So now is a very good time to be studying this, and there's a small asterisk. Okay, so 4, fine, but actually there are more than 4, maybe a dozen or so low mass, basically isolated planetary mass objects that are known, so maybe far away from their star, are really isolated. So this number sort of, in that category, there are a few more objects, but really in this strict category of a gas giant, like a Jupiter-like object, not too far from its host star, there are only 4 that are known that are accreting, so still forming. Okay, because we want to all be on the same page, let's do a very quick overview of gas giant planet formation in 2 slides. People spend, of course, the whole career studying this, but let's do it in 2 slides. So if we take, so when I flew here from basically Germany, from Europe here, I was able to take this picture from the plane. We were just a bit higher up, right, of course. So if we zoom in a bit, what do we see? Yes, Taipei, very good, okay. But let's look a bit further away from the sun at some molecular cloud, which is somewhere. So you have this big cold gas and dust structure, and if you zoom in, you have a zone which is even colder and denser, called a dark cloud, basically. And if you zoom in further, then you see some region which has started collapsing on itself, and you see that some young bright stars are being formed. And if you zoom in some more around maybe one of these sort of not too high mass stars, you'll find a star in its center at a later stage with a gas and dust disk around it. And right here in the P, the whole of the letter P, there's a planet maybe which has opened a gap, and this is where planets are forming. So this is just a one slide overview, right, of the scales we're talking about, the planet formation idea. And the planet formation process itself leads to the result that you have maybe some leftover ring of dust and gas, and here also some dust emission from these planets. So these are two different stars, both of which have an accreting gas giant planet. And actually, there are two. So this is the famous star system PDS 70 B and C. And WSP 2 with the second planet is this very faint dot, or not so faint, but very small dot, basically extremely close to the star, which was not quite visible in the original image, but it turns out that there's a second planet. And both of them here are accreting, and this second one we don't know, it might not be. But so these are small numbers, but growing. And as I was mentioning before, there are also some isolated accretors, and this is just a very brief overview, a small subset of what you can study. So you can study very high resolution line profiles for H alpha here. This is imaging in H alpha. You can study the time variability. You have the whole spectrum and very many different hydrogen lines, all tracing accretion, different profiles, changing over time. So it's just to make the point, it's not, the details don't matter here, it's just to make the point that this is an active field which is developing with these isolated or semi-isolated planetary mass objects. We'll be looking more at the real sort of these kinds of objects. So of these, there are only two, but there are a few more that are the same wider category. And now the second part of the planet formation, and just to give a brief idea, this is maybe the timeline. So if you say around 0.1 mega years, 1 to 10, 0.1 to 10, and 10 to 100. So you start with dust particles, so at a small size, that's the vertical axis. By some process, the dust clumps together and is able to form bigger objects. There's a runaway growth, which happens at some time because of a feedback, basically. And then one sort of object gets lucky and starts forming what will ultimately become a rocky planet, so gas-free, essentially. Or if the gas accretion rate is large enough compared to how fast the gas is being dissipated, then it will be able to assemble into a gas giant planet, which is larger and more massive and dominated in terms of mass by gas and not by solids. So that's just the one slide or two slide overview of planet formation. And while this gas to form a gas giant is being assembled, this is where the stage at which these hydrogen lines and other metal lines also actually are being emitted, and this is what we want to study because it's telling us something about this formation process, about how fast, how much, where, and how this might depend on the planet mass, and so on and so on. If we were able to do with statistics, which is currently hard with 4 only objects, of course, but this will grow hopefully with time. Okay, the exoplanet population, to give a brief overview. So in this talk, we're focusing on gas giant planets, but actually most planets that we know, so these 6,000 planets basically, are mostly known from the so-called transit method and radial velocity method. So this is a diagram, this sort of standard diagram showing the mass of the planet against separation from the host star. And here you have the transiting planets, which cover a range of masses, but are all relatively close, just because, right, you're seeing the light of the star dimming periodically as the planet happens to be crossing, to be passing in front of it from our point of view. Works only for those systems where the planet is basically in our line of sight. And so, of course, the probability of catching a planet passing in front of its star is much higher if the planet is closer to the star, because further out you need extremely precise alignment. So that's why there's a strong bias towards smaller separations. And actually, this region of the diagram is basically incomplete because we cannot observe them by the planets here. We cannot detect them by transits, also not by radial velocity, where you see the radial motion of the star, the reflex motion from the planet around it. That's also less sensitive further out. But so with these two techniques, basically you cover this part closer in, and then there's the direct imaging, where you're really detecting light from the planet itself, the photons coming from the planet. So of course that's more sensitive to planets that are young and still bright. But in that case, the bias is towards large distance planets because you're further away from the glare of the central star, and so it's easier to see the light of the planet. And again, once it's, if it's higher mass and or younger, it will be brighter and therefore also easier to detect. And this is, tens to hundreds, even thousands of AU as the typical distance we're talking about. And what is even more exciting maybe than this direct imaging, because that's still, we're talking often about contrast of 10 to the 6, 10 to the 7, to the 8, even to the 8 basically, between this planet right next to its host star. So the typical analogy, which is always quoted, is like detecting a firefly next to a lighthouse. But that's really the kind of contrast for some of these systems. The angular separation is really 0.1, 0.2 arc seconds, and a brightness contrast of 10 to the 6 to the 7. So Hiro is the big expert, as maybe there are others in the room, I'm sorry, I don't know, but he can tell you everything about this high contrast imaging, and you need really clever instrumentation techniques and also post-processing techniques to tease out this very faint planet signal from the data. And as a theoretician, I'm always amazed by how much you can do, how clever people are, and you derotate and you use this correlation and that effect and the velocity of the Earth, and you use the number of birds flying across Argentina to determine the density of craters on the moon, which influences it's just exaggerating a bit, but to say how creative people are with these techniques, and it's really pushing down the limits of what we're able to do. So it's very impressive. And to put this in context, right, the first exoplanet, 51 Pegasus B, was discovered 31 years ago, but it's been only 8 years since the first accreting planet was found, so it's still a relatively young field. Okay, gas giant statistics. So as we've been saying, direct imaging is not really sensitive to planets that are close in on this diagram, so it's would be incomplete in terms of this population here. And it turns out that intrinsically, gas giants at large distances from their stars are just intrinsically rare. We were hoping when we found the first directly imaged planet in 2004, we just need to keep pushing the limits and then we'll discover, thousands or hundreds or whatever. But it turns out it's maybe only 1%. There was a big survey, which is, final results will be published soon, the SHINE survey, looking at 500 stars and really, very, very sensitive observations, and only, I think, 5 or 6 or 7 planets are so found, just because they're very rare. It's unfortunate. It makes it sort of expensive to do, but that's reality. And from the formation point of view, if we're looking at ultra-wide planets that are maybe hundreds of AU from their star, maybe they formed in a way which is very similar to a really isolated planet. So that's just to keep in mind, but it's not entirely clear how you can form these planets that are found at hundreds of AU, because if they're formed very close in to their star, which is easier to do, well, how do you get them that far out without them being actually unbound, right? It's sort of, if there's some scattering or so, fine, you kick the planet out, but then it's easier to eject it completely from the system than to park it at 600 or 1,000 AU, so it's not clear. And forming the planets directly in situ there at hundreds or even 1,000 AU is also not obvious, because the time scales are too long, there's not enough mass in this. So somehow it works, but how is not clear yet. And there was this very nice review talk by Brendan Bowler. He was giving an overview of the true frequency, so the number basically of planets is a function of orbital separation from the star. So this is 0.01 to 0.1 AU, 0.1 to 1, 1 to 10, 10 to 100, and more than 100 AU. And it turns out from all these different techniques and surveys that the intrinsic fraction of planets is actually very small. So the number of stars with a planet in this separation range is very small, around 0.5 to 1%, very close to the star. These so-called hot Jupiters, which are easy to find because they're big and close in, but actually they're intrinsically very rare, 0.5, 1%. Warm Jupiters, which are again Jupiter mass, but slightly further out at 0.1 to 1 AU, about 1 to 2% of stars have this. Then there are the cold Jupiters, so more like our Jupiter at 1 to 10 AU. And there it turns out actually that about 15 to 25% of stars have one planet, sort of on average. And this is coming from different surveys looking at different studies. So it's relatively robust as a statistic. Now for distant planets, that's what I was just mentioning before, around 2 to 5% only of stars have planets around 10 to 100 or so AU. And then if we're talking about the ultra-wide planets, it drops back down to about 0.5 to 2%. And very interestingly, this peak in the planet, so the gas giant, say more than 1 Jupiter mass or 2 Jupiter masses or so, this peak in the abundance is right outside the ice line, which is the distance where the temperature, so sort of moving outwards from the star, right? The temperature and the disk around the star is highest, heated by the star and by the viscous heating in the midplane, and the temperature drops, and at some point it gets cold enough that the water is in ice form, and just outside of this location is where most planets are found. And this is thought not to be a coincidence because the water ice line by some formation theories is key to the formation of the building blocks of the planet. This might be reflecting, these statistics, reflecting really the formation process, which is very interesting.
Why not the 100% when I add everything?
Sorry. Yes. This is meant 0.5 to 1%. So these percentages are number of stars or fraction of stars with a planet in this category. So it could be 0 everywhere or 100% everywhere. It's not. Yeah. No, that's right. Yeah, sorry, it's not the number. It's not the distribution of the known planets, but really per star how much is found. Thank you. Yeah. Okay. The ELT. I'm sure everybody has heard about this. Sorry for the tilted workers, but just put this to scale, right? This is the ELT sort of main structure and so on, the primary mirror, of course, with the secondary and so on. And this is 2 people for scale, so that's a bit big. First slide will be around 2029, 2030. And this project, which we did, was looking at specifically METIS, which will be the first generation mid-infrared ELT imager and spectrograph with a spectral resolution of 10 to the 5. So we're jumping now to this specific project. And what can we do with this? One thing is, of course, to study accreting planets. And there the main line is the Brackett alpha line. So let me show you here the sensitivity of METIS. So the residual noise, i.e. a low number here means sensitive. So basically as against wavelength. So we're talking about 2.5 to 4 microns is the L band, and here METIS is a good sensitivity, and then again in the M band at 4.5 to 5.3, and outside of this it sort of explodes, it gets worse because of the atmosphere. And for reference, we're putting here the hydrogen line, so the Brackett alpha series, which is the 5 to 4 line, and the Pfund series, Pfund beta, gamma, delta, epsilon, and so on, and the Humphreys series, starting at Humphreys delta. So the detail names don't really matter. The point is the brightest and the relative heights of the lines are the relative intensities for an accreting planet, roughly. And so the brightest line is the Brackett alpha line, and what would have been maybe the second brightest would have been Pfund alpha, but it's unfortunately outside of the N band, so really not observable. And these other ones are minor, can be studied also, but we'll be focusing on Brackett alpha because this is the main tracer. And the point why Brackett alpha is interesting, or why hydrogen lines are interesting, we'll see very soon. By the way, it's a good neighborhood. This is the ELT seen from the VLT, and this is the VLT seen from the ELT. So they're about 300 kilometers apart. I found this on a slide somewhere, so it's very sort of funny. I think it's taken with normal cameras, not with the telescopes, but I guess with the telescope you could probably count the number of screws, or on this one, right? From the ELT you could count the number of screws on the VLT entrance window or something. Okay. let's take a look at sort of the background problem, or why, you know, what is going on. If we look at a disk around a young star, so the star is in the center, in the simulation it's of course not included, its gravity is included, but you don't need to include the star itself. Here you have a gas giant of a few Jupiter masses, and the torques it exerts, so its effect on the disk is able to open a gap around its orbit of a few times its Hill sphere, basically in width, and this planet is drawing gas from the protoplanetary disk, PPD, protoplanetary disk, onto it, and somehow this gas is accreting. And if we zoom in a bit on this region, basically now take a side view, so sort of in the disk, from the side, you see this global flow of gas falling in from sort of this edge and that side and these arms and so on, falling in towards the planet, which actually on this, at this scale would be tiny. So this is the position of the planet. The black line here is basically, this size, and the planet itself is about 1,000 times smaller, so very much smaller. But this gas, it's coming from these larger scales and then falling down towards the planet. And so this is a schematic view. Once again, now again a side view of the disk. So you have the star around here, this gap which the planet has opened. It has maybe, or probably most certainly has a circumplanetary disk around it. So this is a cut through the side view. You should see maybe the sort of the other side on that side here. It's not shown. It's really just a one plane cut. Planet which is forming, this gas which is falling from the Hill sphere basically onto the CPD, onto the circumplanetary disk, and also onto the planet. And what we want to do is to predict the shape, the spectral shape of the lines that are coming from when this gas hits the CPD and hits the circumplanetary disk and hits the planetary surface. And we're focusing, as I said, on planets in disk that are sort of classical planets, or planets in a classical sense, gas giants like Jupiter. And if we look at a detailed simulation, so you have, again, from the side view, the planet here is this white piece, basically. And so the gas is coming in along these flow lines and hitting the surface of the circumplanetary disk, which extends much further out, and also falling on the surface of the planet. And what we're going to do actually is to use a semi-analytical approach, which is backed up by simulations, but it makes it possible to vary parameters very easily instead of having to run simulations for every parameter combination of interest. And we're looking at the limiting case of no magnetospheric accretion. So in star formation, and also for planets, it's thought that if the planet, or the central accreting object, has a strong enough magnetic field, it can actually disrupt this circumplanetary or circumstellar disk. It's the same problem, just scaled, basically. And then the gas will be flowing onto the planet by some magnetic field lines and so on. So we won't do this. I can give more details if somebody's interested. It's a very interesting topic, but we're looking at the limiting case, which will apply to some systems some of the time, that there's only pure infall basically onto the planet and its circumplanetary disk, and there's no magnetospheric accretion process going on. So if we zoom in here, we have the following. We have these, again, just to make it clear, we have this gas flowing along these lines, different colors, just 1, 2, 3, 4, 5, 6, 7 degrees and so on, and hitting the circumplanetary disk surface and hitting the planetary surface. And basically these regions here will be generating these hydrogen lines and metal lines, but the brightest ones are the hydrogen lines. Okay, and how is this happening? How do you calculate the emission from an accretion shock? So this is the shock emission models of Yoshiko Aoyama. And it's complicated, right? So it's a non-equilibrium process. The gas is actually post-shock, reaches extremely high non-equilibrium temperatures. The cooling starts to happen by collisional excitation. There's H2 dissociation, H2, so water line, rotational lines are cooling the gas. These different hydrogen lines are being formed because the electrons the different energy level, electron energy levels are starting to be populated, and out comes a line shape and so on. So if we just sort of simplify things, make this a bit blurry, the higher level view is the input is some pre-shock velocity and density at a small patch, at a small region, and out comes a line profile and a total flux. And that's, so the details were Yuhiko's PhD work and done beautifully, but for the sort of user, in our case, for us, we just need to know what the local pre-shock density and velocity are, and this model tells us, and it's basically, it can't be wrong because it's the hydrogen atom. It's still not very non-trivial to do because you need to consider many different energy levels and do the time-dependent reactions and so on, but it's the hydrogen atom, there's no sort of uncertainty. We know everything about it. And then, to calculate the total line coming from this accretion shock, you just need to integrate spatially because, of course, there's a slight distribution of velocities and densities on the surface of the planet and the surface of the circumplanetary disk. When the gas is hitting, it's falling at slightly different velocities and densities. And so you can calculate this with the semi-analytical model at every location and then integrate spatially to know what the total line shape will be, because we cannot resolve the planetary surface and the circumplanetary surface. These scales are too small. These are tens of micro arc seconds, and the ELT, the extremely large telescope, right, has a beam of 26, in this case 26 milli arc seconds, still factors of 1,000 bigger. Okay, if we still take this this view of basically a forming planet, so what we're doing here is we're zooming in onto the planet. This is this bright yellow thing seen at 45 degrees inclination, and this blue surface is the inner parts of the circumplanetary disk. So this is in micro arc seconds, right? It's not observable. Just to put it in scale, if we put it specifically at the distance of PDS 70b, one of these famous accreting systems, just to put in context, but it's very easy to scale. So the circumplanetary disk goes out maybe that far, but the emission is coming only from the surface of a planet and the innermost parts here of the circumplanetary disk, because what is falling outside is falling too slowly to emit any lines. So the color here, so this is one planetary radius here taken as 2 Jupiter radii, which is fine for forming planets. This color here is showing the pre-shock velocity of the gas, so it's highest at the pole, the gas which is falling in free fall directly onto the planet at 94 kilometers per second, and towards the equator gets a bit weaker, drops down to maybe about 60, 70 kilometers per second. And here on the surface of the circumplanetary disk, the gas which is falling, because it's the other component, it's the theta component, but these are details. Here the velocity is more like 30 to 40 and then just dropping down and becoming sort of irrelevant for the line emission further out. And if you compute at every location the flux, so this is now the intensity in energy per time per square area of a detector at this point, and per it's spectrally resolved and so on, but so these details matter. It's just the intensity don't matter, it's the intensity. The intensity is highest at the pole, but the area is also smallest at the pole. So it will, the main contribution is coming from these mid-latitudes, it will turn out for the total line shape. But so the local intensity is highest here because of the highest velocity, and then dropping down again on the CPD, circumplanetary disk surface, which extends. You see only the innermost parts are bright and the rest gets fainter, and even though the area is increasing as the square of the distance, right, just a simple area, the local intensity is decreasing very quickly to zero, so these regions will not contribute to the total line shape, and that's why we can focus on this part. One thing to talk about is actually the accretion rate, right? Because we say, fine, the gas is falling on the surface of the planet, the surface of the circumplanetary disk, but how much gas is falling? And one important point is that, I don't want to go into all the details, but I just want to make quickly the point that the gas which is falling on the planet and the circumplanetary disk is maybe this whole sort of region, but the part that is emitting lines is only the innermost part. So there's a distinction to be made between what is falling in total onto the system and what is actually emitting lines. That's just the point I want to make here. I'll skip the details for now. Okay, so now let's look at one example already in detail. I mean, we've started doing this with these specific numbers I was quoting. So the nominal case of PDS-70, reasonable masses and radii and temperatures and so on. The details don't matter, just for reference. There are a few free parameters, these, but really not many more. And typical distance to a star-forming region and specific distance here to PDS-70, 113.4 parsecs. And this is the outcome. So if we integrate if we integrate this line emission, so here we're showing just the brightness at the center of the line of bracket alpha, but of course we have this as a function of wavelength. So if we integrate this spatially at every wavelength point, we have the following. So this is the flux against the wavelength, here expressed as a Doppler velocity offset from the center of the bracket alpha line, which is this dashed gray line. And you see the total line shape which comes out is this black line, and it's actually slightly redshifted. So the dotted line is the bisector of the line, so the middle point horizontally calculated at every height. And you see that it's slightly redshifted. And this is not a coincidence, it's because the line emission is happening in this post-shock region where the gas is systematically moving away from the observer slightly. What you see also is that the line here is about 30 kilometers per second wide, but the free fall velocity from infinity is more like 90 kilometers. It's this gray line. So the line is actually much narrower than what one might have guessed. You would have said, okay, fine, I can somehow calculate the total line flux, and then, well, the line width must be somehow the free fall velocity, so then you would draw simply this red line. But if you do the detailed computation as we have done, you find that actually the line is much narrower, which makes it easier to observe ultimately.
Gabriel, so yes. For that plot, you haven't applied any instrument?
No. Well, if you want, yes, I have. There is none. Okay. Because with the so the resolution of 10 to the 5 of METIS is 3 kilometers per second. So there's no finer detail that gets washed out. And that's the beauty of, thank you very much. That's the beauty of METIS. So there are other spectrographs that exist, but at much lower resolution. 2000 or so would smooth the line, broaden the line to something like this. Whereas with METIS, you can observe the full resolution. But we need still to take care of the noise to talk about this, so we'll do this. One source of noise actually is the continuum, so the continuum emission from the photosphere of the planet, right? The typical temperatures of these forming planets is some 1,000 to 2,000 Kelvin. And so there is some emission at bracket alpha, which is at 4 microns. And the colored lines here are from the sort of only high resolution models. This will change soon, but basically there are not many high resolution models available freely online because nobody has really looked at these very high resolutions in the mid-infrared basically. For 3 different effective temperatures, but then scale again to have the same flux corresponding to the observations. The point is just to say, if you look at the pale lines, this is the intrinsic photosphere, so coming from H2S and H2O and different molecules, you have these absorption troughs coming from the atmosphere of the planet, and then on top of this, you'll actually be adding this black line, which is the line shape coming from the shock. So it's this black line here and dashed. So what we find actually is that the peak excess, the peak shock, peak excess, yes, is about as high as the photosphere. So the true observation will be sort of photosphere plus the line, and again the photosphere. So it's about the same height, which is too bad in the sense that it would have been nicer if we had found that the accretion line is 10 times brighter than the photosphere from the planet, right? It would have made it easy, but it could have been much worse. It could have been that this accretion line is only a tiny blimp, which you could never pick out from the photosphere. So it's, okay, fine. And what actually helps, so if you play with the parameters, you can make it more observable, a bit less, but not by orders of magnitude, or not many. What helps actually is the rotational broadening, because young planets are spinning at some non-negligible speed, maybe 10, 20, up to 30 kilometers per second. So it's a bit of an open question, but there are some observational data on this. And then, and that's why there are these brighter, thicker lines, this is those pale, faint, intrinsic lines, the models in the background, smoothed by the rotation to 10 kilometers per second. So the rotational broadening of the atmospheric, photospheric features makes them much shallower, and therefore lets the shock stand out or be easier to, put it differently, makes it easier to subtract the photosphere from the observation to back out the accretion line. Because it removes the structure, right? The flatter it is, the easier it is to remove this photospheric background. And now if we put this together, we get basically the black line. So again, this yellow line, this is now again still for Brackett alpha, but now a wider wavelength range, just to give the sort of spectral context. Again, the flux, but on log scale, but okay, a small range, so it's almost linear if you want. This yellow line is again the rotationally smoothed, broadened photospheric signal. The red is the shock line, and black is the sum of the two. And in gray are actually error bars, which you will get from the detailed simulations of Roy, basically, which agrees with what Hiro is doing. And it's after 4 hours of observation, you will get these kinds of relatively small error bars for the fiducial parameters for PDSME. So this is our prediction for what we'll see for this planet. Of course, in reality, it might be a bit different. Actually, whether the atmosphere really looks exactly like this or whether the lines are different is not known. So it's a big topic of active research in planetary atmospheres, what the real line lists of water and H2S and all these molecules and methane and so on are, because that changes a lot. Actually, the exact position and width and depth and so on of these features, but this will be somehow, this is somehow typical, so it won't be that different. And then if we compare the signal to the noise, so this is the signal to noise per spectral bin for the wavelength bins basically of METIS of the instrument, you find here that the peak signal to noise after 4 hours of observation, put differently. Yes, this is the bin for 4 hours. The signal to noise ratio for 4 hours, the peak is around 15, which is nice. It's not 100, it's not 1,000, but it's also not 3 to 5, so it's a very clear detection. This is just for reference 3 and 5, right? So the central part of the line will be clearly observable, and these gray lines are actually where so I didn't mention this, but in the center of the line, the shape is Gaussian to 10%, and it's only outside that the wings are actually a bit wider, but we won't be able to measure the non-Gaussianity of the line wings here outside of these gray lines, because the signal to noise will be only around 3 or 4 or 5 in the best case, so it's not very realistic. But it still means that with only 10 minutes of observation, you can get a 3 sigma detection of the peak, or after 4 hours, 15. So it's just a simple square root of scaling between the two axes, but it's saying that it's very easy to observe the Brackett alpha line for accreting planets for PDSME specifically, and this will be very similar for all other of the 4, so the 3 others basically, 3 other planets. And if you remember one of the first plots, there's not only the Brackett alpha line, there are other lines, so the Pfund beta and Pfund gamma and Pfund delta and so on. So if we repeat this exercise for the other lines, it turns out they're not really observable. So again, in every case, the red line is the shock signal, and on a linear scale now. So the shock signal, and the yellow curve is the photosphere, and black is the sum of the two. And you can tell, right, for Pfund beta, okay, fine, there's an excess. If we know precisely what the photosphere is, yes, we could subtract it and get this red shape back out, the shock excess. For Pfund gamma, I think forget it, right? It's a tiny thing, and for Pfund data, delta even more. So it turns out that only Brackett alpha is really bright enough compared to the photosphere, and given also the noise of the instrument. So the noise is basically, it's not very different from wavelength to wavelength, but the photosphere just turns out to be locally much brighter at von gamma, and these higher than Brackett alpha, and these higher order lines are all intrinsically fainter than Brackett alpha. And now we can repeat this exercise, or just vary the parameters. I won't go into all the details, but the point is you can vary basically the accretion, surface density, but it's really the accretion rate, ultimately, the inclination, the thickness of the CPD, the planetary mass, planetary radius, and just comparing the different line profiles. And in every case, what we're doing is we're normalizing to the peak. So this is the normalized line profile. And here the percentages, plus 30, minus 30%, and then 10 and 15 and 20 and so on, just showing the change in the total flux in the line. But it's to make the point that even as you change the planetary radius from 2 to 1.5 to 3 Jupiter radii, so some small but really the expected range of values, or the thickness of the CPD, the shape of the line is not changing. So the total flux does, but the line shape doesn't change. So even with no noise and even with a great resolution of METIS, it will not really be possible to, just by the line shape, infer what the inclination, what the thickness of the disk is, what the inclination is, the mass and the radius, so these different parameters which affect the total line flux will not be possible, just because the line shape turns out to be too similar, even as you vary the parameters by some range of values. And if you're wondering, the dashed line in here, which is always smaller, is just showing the relative contribution of the circumplanetary disk to the total line shape. So this is the total line coming from planetary surface and the CPD, and this is yes, that's right, and this is only the contribution of the CPD. So as you increase the mass of the planet, the contribution of the CPD can reach about half at 20 Jupiter masses, which is already sort of on the high side. It's more a brown dwarf maybe than really a planet, but okay, that's just a name to some extent. But basically you cannot constrain the parameters just from the line shape, which, if you want, is unfortunate, but that's what it is. Yes, and right, and I didn't explain this, but the m dot we're assuming is made to reproduce the H alpha, which has been observed. So Brackett alpha hasn't been observed from these planets, right, for these objects yet, but we have several H alpha measurements, and it's variable over time. So we picked an optimistic limit. We took the highest value, so highest H alpha value, what Brackett alpha basically corresponds to this, or we've used our model, yes, to reproduce the Brackett alpha. And if we increase the accretion rate by a factor of, so this is the standard case in black, and if we increase it by a factor of 10, the whole flux increases by 0.9 dex, right, and so on. But still, it doesn't change the shape yet. Is that okay?
Yeah.
Thank you. Microwave, popcorn, or something? It's a movie theater here. Okay. Coming to slightly the end, one more point is, of course, could worry, what about the star, right? So let's take half a step back. This is the orbit of PDS-70b, so the visible, the projected apparent separation from the host star in arc seconds. So it's currently, so we have the year 2026. It's currently at 140 milli-arc seconds from the star, and PDS-70c is a bit outside ND, which probably isn't a planet, it's even closer in, but fine, we're looking at this. And this is the orbit in the future. So unfortunately, when the ELT will come online in 2029 or 30, PDS-70 will be even closer and getting closer to the star, but this is the minimum, right? It goes back out. So the minimum is in the year 2034, and then the separation will increase again. But it's not even a problem, because if we look at the contrast curve for the METIS instrument, so this is basically the sort of residual noise from the star. So anything which is less bright, so then vertically is basically a scaled brightness, a relative brightness. So anything which is below this curve is not observable, but PDS-70b is very likely, is absolutely brighter than the noise coming from the star, even as it's moving. So these are the different epochs. It's currently and in 4 years and so on, 2034, moving back out. So it never gets closer than 115 milliarc seconds. What is dominating the noise is really the background from the telescope and the instrument and the atmosphere. So all of this is brighter than any residual star light or star noise, really. So that's not an issue at these separations. This is for reference 1.22 lambda over d, right, the classical diffraction limit. So we're very clearly in the background limited regime, not in the diffraction regime, because the ELT is a 39-meter telescope, right? So at 4 microns, this corresponds to 26 milliarc seconds, which is much smaller. So that's not a problem. And then basically the last slide, we can vary the planet mass and the accretion rate. That was your question. So this is our fiducial case for PDS-70. And at every position, calculate the peak excess coming from the flux, from the shock, sorry. So it turns out that it scales mostly with the accretion rate and actually not very much with the planetary mass. And you can draw contours of how long you need to have a 3 or 5 sigma detection. I don't remember which number we picked, but basically 3 sigma. In 15 minutes, right, for PDS-70, you have a 3 sigma detection of the line, and at lower accretion rates, therefore lower line brightnesses, it takes more time, and down here you can forget it. But so you can vary these parameters, and for any planet of interest, it's a semi-analytical model, so it's very quick to calculate. You can predict what the peak excess is and how long is needed to have a detection of the line and of the signal to noise per spectral bin. And the main parameters are really planetary mass, but which turns out not to play so much of a role, which is not, it's not so much dependent on it past 2-3 Jupiter masses, and the accretion rate is the main one. And that is probably variable over time. So, even if you don't get a detection at an epoch, please try again later. You might just get lucky and it will be 3 times brighter, 3 times fainter, and that will help if it's brighter. So in summary, we've calculated the line emission from the shock at super Jupiters, so several Jupiter mass planets that are observable with the METIS instrument of the ELT. And the shock at the planet's surface dominates, and you add to this shock on the surface of the CPD, and then you integrate this spatially to calculate the total line profile. So it's a very simple idea, and we just did it for all these different, as a function of different free parameters. And a point I didn't mention actually is that, what about extinction? But we're talking about super Jupiter planets, so several Jupiter masses, and they have most likely opened a gap in the disk around their star, as we saw in one of the introductory slides. And so extinction in the gap is probably not much of an issue because of the reduced surface density, so both of dust and of gas anyway. And one point to keep in mind is that if the planet is spinning, as it probably is, while it's young, this moves the photospheric signal and helps the line signal stand out. And PDS-70b, specifically in our prediction, should be very detectable with a high signal to noise ratio in per bin in half a night. And there are other targets, so the WISPIT-2 planets, which is this other system B, possibly C, it might be accreting also, and whatever will come out of the data release 4 of Gaia, so in December 2nd, I think. There are predictions that 2,000 planets will be sort of instantaneously discovered, and with data release 5, 21,000, because you're looking at this very precise astrometry of the stars. So for many of these planets, they will be young and could be also accreting. So the future will bring more planets. I just want to end with this nice view. So of course now the telescope, the LT is much further. So it's a still frame from a beautiful movie showing a sunrise, or maybe time reverse sunset, I don't know, behind the ELT. So you see, these spots on the surface of the star, and it's moving. It's just a beautiful movie, which you've maybe seen. And I want just to say, 谢谢.
Thank you very much, Gabriel. So, okay.
Yeah, very interesting.
Thank you.
So for star formation, float stars usually info accretion go to the disk, not to star directly, massively cause the out or whatever. For this case, why material can still go to the planet?
Yes, thank you. That's a very good point. And the answer is most of it does go to the disk, not to the planet. It's only about, I'm not sure I have a slide, but it's only about 1% of the total infalling gas into the heliosphere, right, from these larger scales, right, from basically from this square falling towards the planet or all this gas. Most of this is falling on the circumplanetary disk. And if you look actually, so this thick black line at the heliosphere is at 10 degrees from the pole. And so this line is now a zoom in, 5 Jupiter radii inside, right, this little box here, is landing basically, on the mid-plane. And that's precisely because of angular momentum, only a small fraction is landing on the surface of the planet. And this is the small fraction which is emitting lines. So the rest, so what, outside of about, here 10 or 20 Jupiter radii from the planet, you can have 5 solar masses per second falling, but there will be just no line emission because we're sensitive only to what is falling on the planet and the CPD, and the innermost part of the CPD. And that's a big question, of course, how much angular momentum the gas actually has, right? So that's sort of with the standard Keplerian shear, but in reality, there might be magnetic processes taking away, and winds and jets and outflows, and right, who knows, but yeah.
So you would still expect the outflow as well?
We don't consider it, we don't need it for our specific model. There was one simulation in 2013 by a very good group which found in one snapshot an outflow driven by the planet, and a one-sided outflow. Gressel et al., Oliver Gressel at AIP in Potsdam in Germany. He does very good work, and they were saying, okay, we found it, we're not claiming this is happening all the time, but it's very impressive. Still, an MHD outflow at a planet might happen, might not, might get lucky, depends on all the the numerical details, but also just the microphysics of magnetic fields. And that's not my expertise. I'm not against it, there's no problem with it, as long as you still have, even if you have an outflow, maybe some jet or something essential part, you still need to let some gas hit the surface of a planet and or of the circumplanetary disk supersonically to have some line emission, because we definitely observe line emission, at least at some planets. So as long as some gas is allowed to shock, you can have whatever outflows you want, right? That sort of doesn't affect this model. Yeah.
Okay.
Thank you for the very nice talk, Gabriel. So you mentioned your hydrogen line emission is mixed with the planetary noise.
Yeah, just on.
I love atmospheres.
I know. Sorry, no offense. It's
No.
beautiful noise, but one man's garbage is another man's data.
Yeah, so I'm just wondering, can you interpret it as in you are probing the region where the shock is hitting the planetary photosphere? And if so, can you extract any information like the temperature or even the velocity of the atmosphere?
That's a very good question. So, honestly, to me, it's not clear what the shock exactly does to the temperature structure of the atmosphere. And as you know best, of course, the temperature structure of the atmosphere is what determines what spectra comes out. So this this calculation or estimate, or then if you add the two on the next slide, right, is really coming from two completely separate models. This is the BT settle models, right, computed for an isolated, non-accreting planet with some effective temperature. And then you do all the chemistry and radiative transfer, and out comes the spectrum. And we're completely separately just saying, okay, we have U equals model, which is calculating this cooling and so on not connected to a planetary atmosphere. And then naively, the sum of the two gives this, or zooming in on these different lines. But would the shock, so in this case the accretion rate actually isn't that high, so the accretion luminosity is not very, or the accretion, so the energy flux coming from the accretion is maybe not very large compared to the flux coming from deep down in the planet. So maybe the the temperature structure in the atmosphere is not too affected by the shock. But in the limiting case of a high accretion rate, you might find, but please, you tell me, would this be like an irradiated planet, right? You have this energy input from the shock at the surface of the planet, which is heating the atmosphere and maybe changing the chemistry, changing the photospheric signal because it's got this heat source on top, right?
Yeah, I'm asking because you mentioned their fluxes are comparable, they're about the same.
Yeah, it turns out.
So that's why I'm thinking maybe they're coming from roughly the same.
No, this is,
Or is it completely different?
it's completely different. Yeah, in this case, it turns out, so, you know, here there's an absolute flux in ergs per second per whatever. This is coming from the NB 4.05, so the photometry with NACO for PDS 70. So we have an idea of the flux at this wavelength, and I'm just scaling the theoretical model to match this observed photometry. And then separately, computing the line from the accretion shock, and it turns out to be equal, but there's no deeper, it's two separate observations. And in this case, because the accretion rate is relatively low, the energy from the accretion actually shouldn't really affect the atmosphere. Yeah. But the more general question is interesting whether, the shock heating, whatever heats is coming from the shock, is coming from the shock and going into the planet, how that might affect the temperature structure of the atmosphere and therefore might affect the outcoming spectrum. That's to me a very interesting question, which hasn't been studied. Like naively, I would think it's like a hot Jupiter, right? So a hot Jupiter, which is very close to its star, has this heating, the energy input somehow coming from the star. You can give 5 lectures about this, I'm sure. In this case, it's a hot shock sitting on the surface of the planet that would also change maybe in a similar way the atmosphere. I don't know. Maybe we can talk about this this week.
And a follow-up question, if I may.
I think so.
Just more of a big picture question. So you mentioned this, we don't have many of these accreting planet systems. They're rare, active research field. So the goal is to constrain the accretion rates. And what's the next step? Can you say something about the formation mechanisms? Like, can you distinguish maybe in some systems you need disk instability to explain what you see? Yeah, what's the big picture for constraining the accretion rates?
Yeah, that's a good question. Let me look quickly if I have a slide, really extra slides. This is getting dangerous. No, yes, no. No, okay, I don't have it. Does this work? No, okay. Sorry. The question is, how is the gas getting from the circumstellar disk down to the planet? So there's sort of two main big questions. One is, how do planets form? Is it by gravitational instability, where some part of the protoplanetary disk basically gets cold enough that it just collapses on itself and quickly forms a gas giant by like stellar formation process? Or is it really more core accretion, where you have, which is what I was showing at the beginning, this buildup of dust sticking together, getting bigger and attracting gas and so on. So that's one question, the main formation mechanism, or maybe put more finely, the formation mechanism is a function of planetary mass, of separation, of different mechanisms will be effective at different places. That's one question. And the other question is, how is the gas actually getting from the local reservoir around the planet to the planet? Is it just by this infall from the heliosphere, basically directly onto the planet and then onto the CPD and through some boundary layer, so where the disk, the circumplanetary disk, is connected to it? Or is it through magnetospheric accretion, which was mentioned, where the planetary magnetic field is truncating its disk around it, and the gas is flowing along the magnetic field lines onto the surface of the planet, and that will lead to a different line shape than what we've predicted, right? It just in general would be a different line shape, and I heard a nice talk yesterday about it. And so if we're able to observe these line shapes at very high resolution, we should be able to say, hopefully, which mechanism is effective, and then somehow try to make the connection to the formation scenario. So, but just like that, it's not obvious, right? One aspect, as you mentioned, is measuring the accretion rate, which tells you how much time you have, right? You want to assemble, say, 5 Jupiter masses within 1, 2, 3, 5 mega years. So that tells you already an average accretion rate. In reality, there might be wild jumps, right? Maybe most of the time the planet is accreting at a relatively low rate, and then a small fraction of the time only at a high rate, or is it more constant? And so you have to do statistics, population studies, look at the maybe the line shape and the mechanism as a function of separation from the star, planet mass, metallicity might be playing a role. These are the bigger scale questions, which we hope to be answering. I mean, this is just obviously what we're doing is a very small part of it, but these are the bigger questions. Yeah. Thank you.
Okay, quick question. The last one.
So for PDS-70 and RISC-2, we know that there's accretion from the H alpha.
Yes.
So what is METIS adding to this?
Another line. So METIS is sensitive to 3 to 5 microns, basically, whereas H alpha is in the optical, and it's high resolution. So it's sort of right. This is wavelength 2.5. So most of the emission. So the H alpha is brighter than Brackett alpha, but H alpha is also affected in general by chromospheric activity, which is exciting, beautiful, wonderful, but not related to accretion directly. So if you want to be studying accretion, it's better to look at Paschen beta, probably, but this is not accessible to METIS. And there will be second generation high resolution spectrographs sensitive to brighter lines intrinsically than Brackett alpha. But this is the best we can do. It sounds a bit negative, but it's really the best we can do in terms of studying accretion processes with the LT, and it's a resolution of 10 to the 5. Yeah. So H alpha is nice, but it's just not accessible to METIS, and these other hydrogen lines, which are intrinsically brighter, are also not yet.
Okay. Yeah, we have to finish the colloquium now.
Sorry.
But anyway, he'll be around until
Friday after end of day.
He's a very nice and friendly person, so please catch him.
Sometimes.
Anytime. So his room is in 1107. So yeah. Thanks again for your nice talk.
Thank you for coming.